Okay, so just a couple things people noted in class based on doing the homework. I had a typo. I had 2.28, should be 2.24, and the VL should be 8.9 versus 9.8. I apologize for the typos. I will correct those. The more important thing, though, again, is always sanity check your work. Does it make sense? You can try plugging in something at 0 for time and seeing what you get for voltages and currents and checking it out. But that takes a little bit of work. But an easy check is, do I have a 90-degree phase shift? Does Eli, the ice person, hold true? And as we talked about in the previous video, in the current in an inductor lags the voltage by 90 degrees. The voltage angle is 153. The current angle is 63. Bada boom, bada bing, you've got a 90-degree phase shift. That is indicated by Eli. So this works. So let's continue on. Because we looked at the case where everything was initially uncharged, so our capacitors and our inductors have no charge on them. Now we're going to start to modify our circuit analysis so we can include initial conditions. And hopefully what you recall, is in the case of a capacitor, I keep forgetting to switch to red. In the case of the capacitor here, the initial condition, you can have it represented as voltage or current, but remember, in a capacitor, V of 0 minus equals V of 0 plus. We did a tremendous amount of work to go ahead and say initial conditions, right, when we did the T 0 minus, T 0 plus, T of infinity. And what we saw, it was usually easier to do voltages because there was no change between the 0 minus and 0 plus. If we do IC of 0 minus, we have no idea if that's going to equal I 0 plus, so we'd have to do additional work. So generally, it's better to do your initial condition modeling of a capacitor with a voltage source. Okay? You can do it with a current source, but you're going to have to do more work. With an inductor, you have our initial charge state of an inductor is indicated by what? Voltage. Well, you certainly could say it's V of L of 0, but VL of 0 minus, does it equal VL of 0 plus? I don't know. It may, but it might not. So using the voltage approach could be a little bit dangerous and might lead to more work. But we do know that that current must equal the initial charge value. So again, with an inductor, it's much, much more efficient to model your initial conditions as a current source, an inductor. So voltage source, current source in an inductor. All right? So we've got our two equations here. We've got VL and VC. In the case of the inductor, we're going to take the Laplace transform of both sides. And remember when we said we just take the derivative of something in the time domain is the same thing as multiplying by S in the Laplace domain? But what we didn't necessarily include, or we've kind of dropped off a little bit, was the fact that we had to subtract the initial condition. So if we want to model the initial condition, all we have to do is not neglect its value. Okay? So if you have an initial charge state on your inductor, all you have to do is show what the current source is, multiply it by L, and then it gets subtracted. Okay? In a capacitor, we're going to integrate, and it's the same thing where we have our current into our capacitor, and then we add to that the initial condition, how much charge has been stored on the capacitor, which is the integral of the current, through whatever time you had before up until your switch or your circuit gets energized or transitioned, whatever the right term is. So you would actually have that initial condition. So what we have is a current source and a voltage source. In the case of the inductor, we're multiplying the initial condition by L. In the case of the capacitor, we take our initial voltage and we just divide it by S, which kind of makes sense, right? Because if you recall, at least from the capacitor's perspective, if I have a DC source with some Vn of t, do you remember what that became in the time domain? Vi of S over S, right? So that initial condition is VI of S over S. In the case of the current source, because we're trying to go from a current to a voltage, we're not going to integrate it. We're just going to multiply by its impedance value that we have. So if I scroll down, here's my voltage. And this is, excuse me, important to note that I'm looking across the entire capacitor. So in the real world, this is what the actual capacitor looks like, right? I'm converting that into the Laplace domain. I should have the same capacitor in there. I should be getting a voltage drop across the capacitor, but I'm modeling its initial condition. So I'm including that capacitor Vc of 0 over S. And because my capacitor voltage is added here, that gets added into this element here. All right? So if I was to do minus to pluses and plus to minuses, you would see that those all get added up. So Vc of S is equal to the voltage drop across the capacitor, 1 over Cs, plus whatever the initial charge is on the capacitor. So those are all additive, so those fully work through. Okay? Questions on that? Let's look at the inductor. So, and I apologize, this might be a little hard to read, but this is the limitation of the software that I use to create this circuit. This is L IL of 0. So that's a time domain quantity. And you'll notice that the voltage drop across the inductor is going to equal that SL that we'd calculated before, right? But now we have to have an opposite sign for the initial condition, for the current. You will note this is not shown as a current source. It's shown as a voltage source, right? But that's okay. We've just converted it by multiplying it by that L value. So in the Laplace domain, the current equivalent with an initial charge is a little bit goofy because we say, hey, we want a current source to be continuously flowing. Well, it is flowing, but we represent that as a voltage source, a voltage that doesn't change. So even though we say that the voltage magnitude doesn't change, it's okay because we've got that LIL of 0. So when we do all our calculations after the fact, it's still going to hold because it's based on our current in the inductor not changing before a transition or just after. Does that make sense? Kind of, sort of? That's the hardest part, is understanding how to locate or how to put the sign terms on your inductor circuit, because it's the opposite. And it all has to do with the math. All right? It all has to do with the Laplace math, because we are subtracting that initial condition as dictated by the math equation here. If you keep track of that, right, you get minus Li of 0. Mathematically, it still has to work to solve our differential equation, which it does work in this case, if we're just keeping it meticulous. So from our circuit analysis perspective, we do that. And here's the advantage. Do you remember how we had to do the t of 0 minus t equals 0 plus and t equal infinity? When we did those analyses, what did we have to do every time we did a t0 minus, t0 plus, t of infinity? What was the first thing we did? We redrew the circuit, right? Guess what? You draw it once in the Laplace. You don't have to redraw. Okay? You will need to maybe perhaps draw it over here so you can get the initial condition calculation. But the t of 0 plus and the t of infinity from a circuit's perspective looks exactly the same. Okay? Because we're not saying that the input is DC, which is going to force the inductor to go to some value. When we do our circuit analysis techniques, because we're actually doing differential equations, we're actually writing differential equations. We're just doing it sneakily in the Laplace domain, right? We're converting those time domain differential equations to the Laplace, which means we can do them algebraically. But we're still being really rigorous in our approach to solving for it. So we don't actually have to do all those games that we have to play where we say t of infinity, t0. We just do it for t of 0 plus, and we have our results. So this actually gives you less work once you get efficient at it. And maybe now you start to understand why, saying, okay, I guess maybe I understand why it's a little bit better to teach circuit analysis with calculus, right? Because you can skip a lot of the steps. Hopefully, for those of you in AC circuits, has John been doing some of the stuff with differential calculus at the very least to show LdIdt or CdVdt, or are they still not necessarily doing that? For those of you who are in 112.
He just like at the very beginning of the class explained like how the units broke out similar to how you did.
Yep.
But other than that, he doesn't really refer to those.
Okay. How about at Eastern Maine? How did you all get exposed to that? Did you calculus-based AC circuit analysis, or it was just steady state analysis? Everything was that? Okay. And it works fine, you know, for many of the applications. It usually just means a little bit more work. That's all. But how many of us will actually be looking at things in the time domain? I mean, if you work in the process control where you're looking at actual dynamic systems, anybody know what dynamic means? Does it mean like, wow, really loud, bubbly person who's really dynamic? Yeah, it just means it's changing. Static means it's stationary. Dynamic means it's changing. These are like words you'll learn as an engineer. Like, what's a deterministic process versus a stochastic process? That's statistics, right? How many of you are taking 232? Nobody's taking 232 yet? One person? A couple people? A stochastic process means it's random. You can't predict with high certainty. You can predict with high certainty, but you can't guarantee it's going to be a certain outcome. Where if it's deterministic, you know that's what's going to happen, right?
I love when engineers just pick the most, like, overly long words to describe something that's random.
That was maybe a mathematician, though. That might have done that, stochastic and deterministic. I don't know, but yeah, random versus know what the value is. Who knows? I'm not sure. Anyway, I get all sidetracked. You can use these models if you want. You will note that they are still looking at your initial condition values as being whatever your 0 plus and 0 minus are. But these will do a better job of giving you currents. So essentially, they're just the Norton equivalents, right, of the previous circuits that we had. So you take the previous circuits here and here and do the Norton equivalents, and you'll end up with those circuits. All right? So let's do an example, and I'm going to sit to try to be a little bit neater with my handwriting. All right, so we have a circuit that's energized by a sinusoidally varying circuit. And we're going to say that the initial voltage here on the capacitor is minus to plus 16 volts. I said I was going to write neater, and it's like it's worse. You got to really support it. So it's minus to plus 16 volts. So what we want to do now is we want to do analysis of the circuit and see if we can solve for I of t and Vc of t for any condition, right? Whether it's time t equals 0, t equals 1, 2, 3, all the way up to infinity. We already know what the initial condition is, so we don't need to draw the t equals 0 minus, right? Because we're told what the initial condition is on the capacitor. So at this point, we can start to figure out what our t equals essentially any time, right? Circuit. And we're going to do that in the Laplace domain. So this is going to be a function or a power supply whose value, what is S times omega equivalent to in the Laplace domain? You remember?
Omega over s squared plus omega squared.
Very good. Omega over s squared plus omega squared. So 40 sine of 4t, I can just multiply the 40 out front, right? Because multiplying by a constant in the time domain is the same thing as multiplying by the same constant in the Laplace domain. This value is omega, so this is 4 over s squared plus 4 squared. So I end up with 160 over s squared plus 4 squared. What does a resistor look like in the Laplace domain?
Or resistor.
A resistor. Any initial condition on there? Last time I checked, resistors can't store any energy, right? They just dissipate. That's their job. Now my capacitor is converted to the Laplace domain. Again, remind me, I forgot.
It's 1 over CS.
1 over CS. So 1 over C over S is 1 over 1/12 times S, which is 12 over S. Pretty clever to use the 1/12, right? Instead of saying some random number, just do 12 over S. Now I've got to include that initial voltage source. So let's go back up to our model of our circuit. And we're going to just add the voltage source, the initial condition of the capacitor, with it being divided by S. So this becomes our initial condition. We said it's 16 volts, negative 16 volts. So this is negative 16 over S. And it's plus to minus in this direction here. If you don't like having a negative voltage source, what you can do is take that out and then just do minus to plus, and that becomes a 16S. Okay? So for any time, right, our t equals any time circuit, we have the Laplace domain equivalent. So we need to do two things. We need to solve for I, and we need to solve for VC of t. I'm going to do that by solving for I of S. And what's the voltage drop across the capacitor? Which circuit which circuit elements should I look at to get VC of t? Or VC of S?
The entirety of the capacitor and
Yeah.
the source.
I got to look across here. And we're going to assume that it's plus to minus in this direction. Okay? So the first thing we'll do is we'll solve for I of S. I of S, actually I won't say equal to, let's do the whole thing out so you can see what's going on. So this is minus to plus, plus to minus, plus to minus, minus to plus. So I have negative 160 over S squared plus 4 squared plus 4I of S plus 12 over S I of S. And then that becomes minus to plus, so that's in the same direction. So minus 16 over S is going to equal 0. Everybody see that? Let me zoom it, bring it up over here so it's a little easier to see, and I've got a little more room to work with.
Why is it a negative 160?
What did we say when we did KVL back in chapter, was it 1 or 2? We said the sum of the voltage drop is going to be equal to 0. So I asked you if a rise or a drop was going to be positive or negative, and you all said a rise is a negative number. Isn't this a rise in the direction of current? So that's why it's the negative. We're just sticking with our convention. So I'm going to bring our terms to one side. So I have I of S times 4 plus 12 over S is going to be equal to 160 over S squared plus 4 squared minus, or plus I should say, 16 over S. I got a bunch of fractions in these equations, and what's the best thing to do? Is get rid of some fractions as much as we can. So I'm going to have I of S times 4S plus 12 over S equals 160 times 16 over S times S squared plus 4 squared. All right? Now, I know that I've got something here that's not 1 that multiplies the S. So I'm going to factor out a 4 and then divide both sides by it. So tell me if this is too quick. I of S times S plus 3 over S equals 40 times 16 over S times S squared plus 4 squared. You buy that for $1?
Is that an S?
The 2 should be,
S plus 3.
the squared should be inside the parentheses, right?
Yes, should be inside the parentheses. Thank you. Did I skip too many steps to come up to this, or do you feel pretty good?
How come it went from 4 plus 12s to 4s plus 12?
I put it under common denominator. So you can see here, I need an s here.
Okay, so you times
So I
it
multiply
s.
that by s. So I just put it under common denominator, trying to get rid of my fractions. Anybody confused? Ask questions, don't be shy. Yes, ma'am.
The 160 over s squared plus 4 squared plus 16 over s.
This side right here.
Yep.
So all I did is I put it under common denominator. So I just multiplied. Actually, this is, you're right. This is bad math. This is, should be plus. No, wait a minute. I did this incorrectly. Let me do this again. I'm not following algebra. So this should be 160, whoops, 160 times s plus 16 times s squared plus 4 squared. I can't just multiply them together like that. I had a brain cramp. Over s squared plus 4 squared times s. Now I can divide both sides by 4, so I have 40s plus 4 times s squared plus 4 squared all over s squared plus 4 squared times s. That's my s value. So now I'm ready to solve for I of s. If I invert and multiply, so I'll do that up over here. I of s is going to be equal to, let's see, 4s squared plus 40s plus 4 squared over s times s squared plus 4 squared times s over s plus 3. So I kind of reworked the numerator a little bit as well, just to have it from my higher terms on the way down. I can see my s's will cancel, and what I'm left with is 4s squared plus 40s plus 16 over s squared plus 4 squared times s plus 3. That's my I of s. Okay? What do I do next? I have I of s. What do I want? I want I of t, right? So how do I go from I of s to I of t? Do I make it look like the table? Not yet. I have one intermediate step. I have to do partial fraction expansion, right? Because I have 2 f of s multiplied. So that's going to be equal to a at an angle of theta over s squared plus 4 squared plus b over s plus 3. And that's it. I'll solve for a at an angle of theta is equal to 4s squared plus 40s plus 16 all over s plus 3. What do I evaluate at again? I'm looking for a at an angle of theta. Close. 4j. Yeah. Positive 4j, right? Because if it was 2j, then omega would be 2, but omega is 4 in this case. So I have 4j. That's equal to a number. And then b is going to be equal to 4s squared plus 40s plus 16 all over s squared plus 16. Evaluated now, we run it at s equals minus 3. And does anybody want me to get the numbers? Because they should be in the slides. Or do you feel like I can just keep it as a at an angle of theta? Does anybody want me to put the numbers down, or do you want me to just treat it as a and b? Okay. So I got to go steal those over here. So a is 32 at an angle of 36.9, and b is minus 4.8. Somebody remember minus 4.8? I'll remember minus 4.8. You all remember 32 at an angle of 36.69. So minus 4.8. And what did I say?
32 at an angle of 36.69.
Thank you. All right. So this now we're going to expand it out, and we're going to just move whatever coefficients we have out front. 36.9. S squared plus 4 squared. What's in the numerator? What needs to be in the numerator?
4.
Omega, right, which is 4. So I have to divide by 4. And then I'm going to add to that plus b. Oh, whoops, not plus b. I'm going to add to that a negative 4.8 times 1 over s plus 3. So now my I of t, I'm just going to make it look like the table, is going to be 8 sine of 4t plus 36.9 degrees minus 4.8 e to the minus 3t. That is my current through my capacitor for all of time, right? All of time after the switch has transitioned. Okay? So now I need to solve for VC of t. So let's go back to here. Right? Okay. So what is VC of S equal to? Well, that's just going to be equal to I of S times 12 over S minus 16 over S, right? That's equal to VC of S. My I of S, I've already gotten down to a pretty good form. So that's going to be equal to 12 over S times 4S squared plus 40S plus 16 over S squared plus 4 squared times S plus 3 minus 16 over S. That is my VC of S. Okay? So fortunately, I've got some of the work already done for me. This is already in partially fraction expanded form. I'm going to have to do a little bit over here for this element. So I'm just going to break this element out and then do my partial fraction expansion there. I could include all of those terms, but I'm not going to bother because what I'm saying is if I did partial fraction expansion, so I know this is an A at an angle of theta, this has some B, this is some C, and then I would add some D to get that there, but guess what D would end up being? It would essentially be the combination of whatever these two numbers would work out being. So all I have to do is solve for it one time, and then I can add it in. So if I just did partial fraction expansion for this and substitute it back in, it works out perfectly fine. So I'm just doing partial fraction expansion for this, and I'll add it in at the end. So that's going to be equal to A over S plus B at an angle of theta over S squared plus 4 squared plus C over S plus 3 is going to be equal to 12 times 4S squared plus 40S plus 16 all over S times S squared plus 4 squared times S plus 3. Please let me know if I'm going too fast or too slow. Is it like Goldilocks? Just right speed? I think it might be too fast because people are like, oh boy, we're writing like mad. Remember, the idea is you don't have to write all this stuff down because all this stuff should be in your notes. You're welcome to do it if that's how you learn. But well, I've recorded it. Yeah, so generally the idea is it's better to pay attention than writing things down. But it's whatever your learning style works best for you. You have the notes in front of you, so all this stuff has already been done out in the notes. So you can append, but it's totally your call. I'm not doing that as a judgment. I'm just trying to remind you periodically that that's available to you. So my A is going to be equal to 12 times 4S squared plus 40S plus 16 over S squared plus 4 squared times S plus 3, evaluated at S equals 0. B at an angle of theta is equal to 12 times 4S squared plus 40S plus 16 over S times S plus 3, evaluated at S equals 4J, and C is going to be equal to 12 times 4S squared plus 40S plus 16 over S times S squared plus 4 squared, evaluated at S equals minus 3. What I need to do now is just make sure that I have the right coefficients. So I'm going to dig through the A, see if I can find those. So let's see. Somebody said 16. I'm sorry. Yeah. So I have this is the same, right? So what I did here, I think I combined them. My I of S I think is fine, but where is?
The next page.
Right, but what I'm trying to do is I'm trying to see where I got, this is my I of S. This is already in partially fraction. But I'm getting a slightly different. This is the correct term, but I have minus 0.8. And that's because when I combined them here, they were combined differently. So it's not 4.8, it's minus 0.8. So this should be minus 0.8. I apologize. This should be just 0.8 and 0.8 and 0.8 here. So let's go back to, do I have the right coefficients or am I not going to be able to do those? I have an A at an angle of, I have a A at an angle of theta, so this one is going to be fine. So I need this one. And then my B term is going to be negative 16, and my A term is that 16 there? Yes, it's 16. So, okay, so I have, so if you folks can help me remember, 16 for the one over the, well, let me see if I can actually do it this way. So I believe this is equal to 16. This is equal to minus 16, and then the other one is 96 at an angle of minus 53. Okay? So at that point, I know, I'll cheat this down a little bit. This is going to be equal to 16 over S plus 96 at an angle of minus 53 over S squared plus 4 squared minus 16 over S plus 3. And remember, I've got the negative 16 over S here, right? So that is going to be added to the end over here. So these two terms have to cancel each other out. Okay? So remember how I said I kept it out at the end, or kept it out at the beginning? So I'm putting it back in there and they add out. So my V C of S is going to be equal to 96 at an angle of minus 53, S squared plus 4 squared, and then that's minus 16 e to the minus, I'm jumping ahead, sorry, minus 16 times 1 over S plus 3. So now my VC of t, right, because this has to be omega, I need 4 here and 4 there. So 96 divided by 4 is 24 sine 4t minus 53 minus 16 e to the minus 3t. And if you check that out, you should be able to get the same results. You can also check here. Remember my current? I said, what happens in the capacitor? What does Eli say? Voltage lags the current. Is that right? Current lags voltage. What is ice? Current leads the voltage. Very good. I'm being a stickler, but hopefully this is going to pay off when you get the power triangles with John. Current leads the voltage in the capacitor. The current has an angle of here, right? Its angle is positive 36.9. This angle is minus 53. So the current, if I was going to draw a phasor diagram, is here. This is I. The voltage is down here. This is 90 degrees. You could also check to see, too, if you plug in V time t equals 0, you should also get 16 volts. Okay? But hopefully that's all summarized correctly here. Okay? So, I got a slightly different, looking over here, I think I had 16. This is 3.2. This is the same. But so essentially what happens, this is the problem when you're doing it, we're doing it two different ways. The coefficients that I calculate over here don't directly translate to the approach that we're doing. So some things have been combined. That's why they're slightly different. But if you check the coefficients, you should end up with a 3.2. So that work that I had over here, that should have been not 16, but it should have been, it's kind of a mess now. That should be 3.2. 3.2. Sorry. It's like it doesn't hold them in place. It kind of moves them along, and I don't know what the rules are like that. Just, I don't know why I didn't just, it's like it's being very specific about where you drag things. Well, I think it's this something here, or maybe it's this guy. I think it's this thing here. When you bring this up, maybe I can lock it. But it's essentially what it's doing, it's creating certain elements. So I don't know, when I lock it, you can see now. Yeah, I don't know. Sorry. I don't know enough about how this software does its things, but essentially what happens is when you draw something like this, you'll notice when I select this information, I hit edit, I think. You'll notice how it highlights separate blocks separately. So what it's doing is it has a file at, the big boxes and then the inside boxes, because when I drew at different times, it keeps them as different objects. And the way that I'm running it, I prefer to keep it all as the same object, but I don't know how to change that, so I apologize. Questions on that?
Paul, how is it 3.2 not 16?
Because the way that I did it here. So if you follow along in this approach, you remember when I had I of s, the I of s here,
Oh, B was 19.2, not 16.
what's that?
And do you have B as 19.2 instead of 16? Because that would give you 3.2 when you did the subtracted the 16 over S from it.
Well, let me just say what I'll say, then we can take a look at that. So when I did the I of s here, you notice how I kept them into two different terms. If you look at, and again, this is going to be a mess, but if you look at my I of s here, I ended up with an I of s that was essentially I of s is equal to 4s squared plus 40s plus 4 over s squared plus 4 squared times s plus 3. So I included that s plus 3 element in there, which is different than what I did here. See how I kept them separate? I didn't do common denominator there. So that's primarily what happens, is just a slightly different way of combining the terms. We'll get the same results as long as you did the algebra correctly. It's just a different way of doing it. Okay? But you would get the same results. You want to do this one for practice and see if you get the same results or was this too much work, the homework that was due today? You want another homework for Tuesday? Don't forget you have a test on Tuesday. So you wanted to, okay. You sure? Want to vote? Well, we can vote and then you can do majority wins. Who wants this problem to be done for homework on Tuesday? Loud and proud. Who does not want it done for Tuesday? Okay, well, I guess we know the answer to that, so. Yeah, you can always practice it. I mean, the other thing too is if you try it and it gets to be a little bit confusing, you can just try it, you know what I mean, and see what happens. But this is going to help you studying for the test because you're doing partial fraction expansion, you're going back to the time domain, yada, yada, yada. It just continues the process on and on and on. So I did show you over here, right, with the numbers that we calculated here. And again, I'd have to go back and see the difference. But you'll see here, when I plug in 0 time, I get negative 16 volts. And what happens to the capacitor when you initially energize the circuit with a sine wave? Yes, well, if it's a sine wave, right, so remember, it was 40 sine of omega t. So if I think about a circuit, let's just draw this. So again, we're trying to get some intuitiveness. So here is 40 sine of 4t. My switch is closed. What was the size of the resistor? Anybody?
Yeah, it's 4 ohms.
4. What was the capacitor? It's 1/12, right? So if I wanted to do this as my t equals 0 plus, right? Let's just do that and check to see what we get. So t equals 0 plus, what happens to this just after the switch transition? 0 volts, isn't it? Because it's a sine wave, so just after you transition the switch, there's no phase shift, so it's a 0 volt signal. So I have this with 4. What does my capacitor look like? It's just a voltage source that has a value of minus to plus 16, right? So what's the voltage across there? Negative 16. What's the current through the capacitor? 16 divided by 4, which is? Which checks out with that, right? So all this stuff should hold together. If you did the t0 minus, t0 plus, t of infinity, you do all that approach, you should get exactly the same results when you do it with Laplace. The downside for this one, though, is we really can't do t of infinity because of that guy, right? That sine wave is always going to be rotating, so it's never going to have a point where it stops. It's always going to be there, doing its charging and discharging, charging and discharging. At some point, though, what you're going to see is this initial condition is going to decay away, and the output voltage and current are just going to be sine waves, right? So this is kind of leading you into the concept of what's called a forced or a natural response. So any of this decaying stuff, right, this DC 16 volts that you have, eventually is going to decay because the resistor, as you run the sine wave through a resistor, it's just going to continue to do that. But you can do superposition, right? Superposition says you've got a 16 volt DC source going through a resistor. Over time, what happens? You're going to decay to zero. So you're going to have no DC source at that point. So it's going to start out kind of looking like this, where it kind of, oops, let's try doing that again. I don't know why it's such a teeny weeny one, but let's try it again. So my DC source is going to go like kind of like, whoops, it's going to go this way. Stop recording. I have not figured out the subtleties of this thing. So it's going to start with a DC, and it's actually going to be, why is this doing that? I don't know what's going on.
Tap that little black dot.
Let's try that again. I think I know what it's doing. I picked too thick of a pen. There we go. We're back in business. So it's going to start out at minus 16, right? So it's going to start over here, and then it's going to start to go up in the sine wave, and it's a 40. So it's going to go like this, and then the next time it's not going to go quite as much, and then it'll oscillate evenly. And so what you're seeing is the decaying DC offset because of the initial 16 volts. Anybody want to do that in multisim? You can check that out in multisim pretty easily. I would show you now, but there's no multisim app for the Apple, for the iPad, so kind of out of luck. But you can do it pretty easily if you want to check it. Oops. I cannot figure out how to grab. There we go. Okay. So let's take a look at another example. So we have this following circuit. So instead of a capacitive circuit, we now have an inductive circuit. What we're going to do is we're going to use this concept of a Laplace domain equivalent impedance seen by the circuit. So we're going to combine that 2 Henry inductor and 6 ohm resistor and combine it into a Thevenin equivalent at that location. And then we can just tack on whatever load, in this case we'll have the 3 ohm load as the value. So the first thing we're going to do is we're not going to energize it with a sine wave. This is actually a 30 volt DC source, so that just becomes 30 over S, right? So let me write that a little more clearly. My inductor is S times L in the Laplace domain, so L is equal to 2, and S is just the variable, so I have 2S there. My resistor is just a 6 ohm resistor. There's nothing happening with that. Now, I'm looking at the Thevenin equivalent at this location, so that 3 ohm resistor has no impact whatsoever to it. So I need to solve for the Thevenin equivalent at those 2 points, and then I can do whatever I want. So I can solve for the voltage, and then I have to solve for Z Thevenin, the next step. I solve for the voltage at those 2 points, or across those 2 points, and then I solve for the impedance. And I'm going to keep everything in the Laplace domain because there's no point in going back into the time domain because it's load dependent, right? Whatever the voltage and the current are going to be on those terminals is dependent on the load. So I'm going to keep things in the Laplace domain. This is called the concept of a transfer function. I'm transferring a circuit element, a load value of a specific resistor, and I'm transferring that to a voltage and a current. And so we're going to start using that concept of, or phrase, transfer function more frequently, because it's going to accurately describe what the heck is happening or how we actually treat it. So my V Thevenin, pretty easy over here. This is V Thevenin of S. What would be the best way to solve for V Thevenin of S? How about or KVL or voltage divider, right? Don't you have a series circuit with a voltage across it? So V Thevenin is going to be V applied, which in this case is 30 over S, time the voltage or the impedance of the element of interest, which is 6, divided by the sum of the impedances, which is 2S plus 6. And that's our V Thevenin of S. A suggestion is to go ahead and try to combine and simplify as much as you can, because when you do partial fraction expansion, it's going to make things a little easier. The only thing I can really simplify here is dividing it by 2, right? So I'm going to have, let's see, 90 over S times S plus 3 as my V of S. Okay? That's what you get here. How do I solve for Z Thevenin? How would you solve for the Thevenin equivalent impedance in the Laplace domain? How about exactly how you would do it in the time domain? You replace ideal sources by their equivalent internal impedance. What does a 30-volt DC source have for an internal impedance? A short circuit. What would that be in the Laplace domain? Still 0 ohms, right? So my DC source is just a short. This is 2S. This is 6 ohms. That is the R Thevenin. Actually, it's better to call it Z Thevenin because it's complex. That is the Z Thevenin of S that I'm looking for. So Z Thevenin of S is equal to the parallel combination of those two elements, right? Parallel combination is product over sum, 12S over 6 plus 2S. I'm going to factor 6S over S plus 3, which matches that result. Okay? So that circuit analysis tool that we've come to use a fair amount, Thevenin equivalent impedances, simplifies it dramatically. So now what we can do is we can entirely replace our circuit that was up here, whoops, that circuit, right, the 30 and all that stuff, and now we're going to replace the 30, the 6 ohm resistor and the 2 Henry inductor, and we're going to replace it with that element. Actually, not even that element. We're going to replace it with this element. This is the Thevenin equivalent. We're going to add onto it at this point our load resistor. We're just adding our load resistor on there. And now all the approaches that we do are correct. So we can solve for our current, I of S. So I of S is going to be equal to our voltage, 90 over S times S plus 3, divided by 6S over S plus 3 ohms. Can somebody shut that door? Because it sounds like people are having a party. I'll shut this door over here. Thank you. Now, you've got fractions within fractions. We'll do this step out a little bit, because the more you can keep your numbers sort of like base numbers, the better off you're going to be. And as we start getting more in the semester, I mentioned it at the beginning of the semester, it's actually easier to work with variables than with numbers, right? Because the numbers you kind of get lost. It's better to use R, L, and C, right? Or to use VN instead of actually using numbers to represent those. But we want to make sure we can go ahead and do that. So the way that How do you deal with fractions and within fractions? Yep. But we have fractions and fractions added with stuff, so the first thing we want to do is multiply by the reciprocal, but we can't do that until we can multiply by the reciprocal, which means this has to be under a common denominator, right? Right? So I put the denominator under a common denominator because it's a fraction within a fraction. Then I can invert and multiply and get rid of some fractions. So my I of s is going to be equal to 90 over s times 9s plus 9, if I have that correct. I think I have that correctly. You'll notice when I inverted it, if you want, I can actually, do you want me to show you the step of how I inverted it, or do you feel pretty comfortable with the algebra to get to this point? Anybody not comfortable, or I don't mind showing it if there's any confusion.
When you have to foil it,
Foil what?
where'd you get the 9s plus 9?
Let's do it out. How's that? Okay? That's perfectly fine. Whoops. So this is 90 over s times s plus 3. This right here, to put this under a common denominator, and maybe I skipped a step and I shouldn't have, this is going to be under a common denominator here, 3 times s plus 3, right? Yeah. If I just multiply that out. So then this becomes, in the numerator, 6s plus 3s plus 3 times 3 is 9, all over s plus 3. Agree with that? Now I'm going to invert and multiply. 90 over s times s plus 3 times s plus 3 over 9s plus 9. Cancel, cancel, equals 90 over s times 9s plus 9. Am I done? What else can I do to make my life easier? Anything that's multiplying the term s but 1 is a problem. We'll actually see for Bode plots we change that up a little bit. So we're going to factor out our 9, so that becomes 10 over s times s plus 1. Did I do partial fraction expansion? Yes, I did. So we're going to do, now we're ready to do partial fraction expansion. So this is going to be equal to a over s plus b over s plus 1. If I'm doing this too quickly to show you how to get a and b, let me know. So a is going to be equal to 10 over s plus 1, evaluated at s equals 0, which is 10. And b is going to be equal to 10 over s, evaluated at s equals minus 1, which means it's minus 10. So that's going to be 10 over s. Minus 10 times 1 over s plus 1 is our partially expanded term there. So my I of t is 10, which is a constant, minus 10 e to the minus 1t. Excuse me. Is it correct? Well, go back to your original circuit. What was the initial condition on the inductor? How much current flow? We didn't put it, right? So we just said it's 0, correct? So just before the switch transitions, just after the switch transition, how much current should be flowing through the inductor? So if I go here and I plug in t equals 0, I of 0 equals 10 minus 10. What's e to the 0 equal to? Checks out. Now we can do the same thing for our voltage. So we'll move that over here for a little room. So the voltage, am I looking for the voltage on the inductor? I don't remember what I said. Oh, that was all we had to do. Find the current through the 3 ohm resistor. Do you know what the voltage across the 3 ohm resistor would be? What would the voltage over the resistor be? You want to do that?
We would just do R times the current at any point in time.
Yeah, we know what the current is, right? We said the current here is 10 over S plus 1. So V3 ohm is going to be equal to 3 times 10 over S times S plus 1, which is 30 over S times S plus 1, which is A over S plus B over S plus 1. A, you notice it's a very consistent pattern, right? I do a lot of the same things over and over again. A is going to be equal to 30 over S plus 1, evaluated at S equals 0. And B is going to be equal to 30 over S when S equals minus 1. So my V3 ohm is going to be equal to 30 over S minus 30 over S plus 1. And V3 ohm in the time domain is equal to 30 minus 30 e to the minus t. Is that correct? Is that correct? Well, how much current through the 3 ohm resistor initially?
Be 0 since there's no current.
There's no current through the inductor, which means going back over here, right? There's no current through this element. So how much current through the 6 ohm resistor? How much current through the 3 ohm resistor? How much of a voltage drop across a 3 ohm resistor with 0 current through it? If I plug in T equals 0 here, what does V3 of 0 equal? Checks out. Checks out beautifully. Beautifully-ish. Questions on how to do these? Because it's all just the same thing over and over again. It's just, you know, it's the same thing in circuit analysis, right? Because in the real world, does anybody have resistors, inductors, and capacitors? Sure, we get them in the lab, but how many people actually build, you know, unless you're building a smartphone or something like that, how much do you actually build that's just resistors, inductors, capacitors, right? In the real world, we have wires, we have motors, we have stuff that does real work for us, right? Changing a little bit because with cell phone technology, my wife was really proud of me. I just changed out our display on our oven. We'd been like for 2 years where you could only see a couple of the actual LED bars, and so you were guessing as to the temperature. You were saying, all right, is the time up or whatever? And it wasn't really useful or practical, but anyway, it was fun for my kids to see like all these resistors, and you know they have a couple of capacitors and all that stuff. So there's more controls like that because we're moving to a world where more electronics control things. But if you think about going back maybe even 30 years ago, where you had some stuff with toys and all that stuff, but think about valves and how they had to move, right? They would be mechanically operated, but you might have an electrical operator do it. Or think about your power steering or your, not your power steering, but your power seats, power windows. A lot of the stuff that we use to make our lives more comfortable is just, you know, we have to interact. It has to be able to move things mechanically. So that's a bunch of wires and metal and all that stuff doing things for us. It's not resistors, inductors, and capacitors. So we just convert those wires and metal into resistors and conductors and capacitors, then we can analyze them. It's the same thing what we're doing here. We're just taking existing circuit analysis stuff. So we've already modeled the circuit as an RLC, and now we're just converting it to another domain to make the math easier. That's essentially all we're trying to do. Okay? So it's very, 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 very repetitive, but the idea is the more repetition you get, the better off you will be. So let's just finish this one really quickly, and then we can vote on whether we should stay or go. We usually will have, in systems, we'll have an input, which is our x, and the system, the transfer function, right, that transfers the input to the output. Most of the time the input is the excitation. The transfer function is whatever the system does. So if you're an RLC circuit designer, it's the RLC circuit. If you're designing a process, filling up a tank, or moving a conveyor, that has an actual process. That has a transfer function. So I excite a tank by maybe turning on water at 5 gallons per minute, or maybe sending a signal, a control signal to a valve to open to a certain percentage. And each one of those inputs or stimuli can be modeled to have a corresponding output, all right? So the G is just how we model physical systems and how we transfer our input to our output. So depressing on the accelerator, right, your car will speed up or slow down depending on what's happening. But it also could be, are you going up a hill? Are you going down a hill? Is the car loaded? Is it not loaded? You can model all those characteristics, and you can model them with G. And then the corresponding output, what the output tends to be after a certain time period, is your output equation. So very simply from a block diagram perspective, I have an input. We do it in Laplace. I have some sort of a transfer function that is indicative usually of the plant. We'll just write it generically as the plant. So again, the plant could be a car, it could be the temperature of a room, it could be a motor's characteristic, it could be a bunch of different things. And then the output is whatever you're interested in. In the car example, it's the speed of the vehicle. In the tank example, it's the level of the tank or the pressure at the bottom of the tank. It can be anything you want it to be. One of the things that's really interesting is biological modeling. You can actually model biological processes. So if you put in a certain stimulus, then you get out a certain response, right? And so there's lots and lots of research for modeling of biological processes, because if we can have an equation that models what's going to happen, how much different would medicine be? How many people go to their doctor and say, I'm sick? What's wrong? My nose is running. Okay. Can you give me a few more details? And so the medical profession is really tough because there could be 10 million things that could be causing your nose to run. But what if you could model the system and say, okay, I'll give you this stimulus, and then your body responds a certain way, hopefully not by death, but some minor response, and then you know exactly what the issue is. That's what we do in engineering, right? I push on something, there's a corresponding output. I can model that. With biological processes, it's not a linear relationship, it's nonlinear. And how do you model all the systems? There's a lot of work to model systems. If I was teaching this class next semester, we would actually model fish population and whatnot, but I'm not teaching the follow-on class this next semester. Yes, sir?
Yeah, isn't there like, I'm not sure if it's through X Prize or something, but wasn't there like someone made like a Star Trek style tricorder that like can analyze if what's wrong with you, like if it, so
I don't know. That could be. I mean,
there is one, but I'm assuming they must be something like this that is able to simulate what's
it could. If I had to guess, it measures your temperature and maybe your blood pressure. But after that, the doctor still, or the physician, whoever's working on you, still has to enter some information to spit out a result. That could be. I don't know. I know when you go to the doctor's office, you talk to the doctor for a few minutes, and they take a couple of things, and they usually go by, okay, what's the most common? And then what's the next most common? You kind of work your way down the list, typically. That's how you treat people, because we're all pretty similar. All right, should we stay or should we go? I've got about 5 minutes of additional time. Do you want your money's worth?
Yeah, so technically.
But that's what I'm saying. If you look at the time on the bottom, it says 1:09, and I stopped it for a second, so we got about 5 minutes left. So who wants more time? Who wants to go for the weekend? One person? All right, have a great weekend.